All right, welcome back. We're going to finish, we're going to do part two, talking about sampling variability and sampling distribution. So, how can X bar or sample population sample mean be an accurate estimate of population mean? So that's what that first little section is saying. After all, different random samples would produce different values of X bar. So what they're saying is, how the heck can I take a sample, look at its mean, and be like, oh, this is an inference back to the population, when every sample can be produced differently? Well, this is called sampling variability. This is an important question to ask yourself. It's a great question, but to make sense of it, we would actually ask the question, what would happen if we took many, many, many samples? So let's actually practice one of those. So again, we originally saw it as population with a single sample and then getting some information from it. But the reality of it is, when we make an inference back to that population, we probably took numerous number of samples to make that inference back. So if we took every one of the possible samples of size n from a population, calculated each and every one of their sample proportions, and graphed all those values, we have what's called a sampling distribution. So we get to create one for ourselves in just a moment. So the sampling distribution of a statistic, blah, 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 is if you take the distribution value of all of the different populations. So again, a sampling distribution is not a single samples information. It's you're talking about something about a population, so you're going to take all of your different samples. Okay, in practice, it's difficult to take all possible samples of size n to obtain the actual sampling distribution. Instead, we use simulations to imitate the process of taking many, many, many samples. So let's see what a sampling distribution is versus a population. There are actually three distinct distributions involved when we sample repeatedly and measure a variable of interest. The first could be a population distribution, which gives the values of the variables for all the individuals in a population. The second is the distribution of sample data. The distribution of sample data shows the values of this variable for all individuals in the sample. And the third, what we're actually working on today, is the sampling distribution, which shows the statistical values from all possible samples of the same size for the population, or a simulated version of all possible samples, since it is impossible more often than not to get every single sample. That is why we do samples. And so let's move forward. Here are our three different types of distributions here. We have a population distribution on the left-hand side, where you see a frequency bar graph right there. Then we have distributions of sample data. So you can see I did an SRS with a trial of 20 on the top, and then an SRS with a trial of 20 in the middle, and an SRS of trial of 20 on the bottom. But what do you notice about that p hat value? I think we're associating p with red in this particular example. So our p hat value of the top one is 8 out of 20, 11 out of 20, and 13 out of 20. And so you can see these are each individual sample set. And then finally, what we are actually talking about are those sampling distributions. So I can get my 0.4, there's one of them right here. 0.55, there could be one occurring right here. And 0.65, there could be one occurring right here. So each of these individual samples is present inside your sampling distribution. But the sampling distribution might be a sample set of 50 or 500 or 5,000 or 20,000 or whatever. Okay, so now it's your opportunity. You get to calculate an SRS about M&Ms and just kind of work through it for yourself.